Okay, sir. So I'll start now then. Okay. So good evening, everyone who has joined with us live for the YouTube session. Today we are continuing with our NCRT solution series for class 12. And today we will be taking up a small chapter, which is semiconductors, electronics. Okay. So as you guys, everyone knows that NCRT plays a key role in your class 12 board exam preparation as well as for NEET aspirants, NEET UG aspirants. Okay. So, so we have been covering all the chapters of class 12. Uh, uh, per day one chapter, all the exercises, detailed solutions. So in that course, today we have reached the semiconductors chapter. This is a total of 6 questions. Most are multiple choice type questions. Okay. Uh, so yeah, this chapter is actually omitted from the JEE syllabus. This is present in NEET UG and your class 12 board exam syllabus. Okay. So before moving further, let me introduce myself. Sashwat Mishra. Uh, I am a third year MBBS student at AIMS Raipur. Previously, I was at IIT-K for 1 year in engineering physics branch, where I got 9.8% CGPA, but I had to drop out and I for pursuing MBBS at AIMS Raipur. So before we move ahead with the session, I would like to give every one of you a small bit of information that if anyone of you will be inspired watching these free YouTube sessions, and if anyone of you wishes to join your regular batches or one-to-one classes with proper guidance and mentorship daily in a proper frame manner for your NEET or JEE preparation as well as class 12 board exam preparation. So the contact number for contacting is actually given in the description of this YouTube video. So feel free to reach out to us for joining one-to-one live classes, batches for your effective NEET and JEE journey. Okay, so that being said, without much further ado, let's begin with today's session, Semiconductors NCRT Solution Series. Great. So here's the first question in front of us. The question says that in an N-type silicon, which of the following statement is true? Electrons are the majority carriers and trivalent atoms are the dopants. Electrons are the minority carriers and pentavalent atoms are the dopants. Holes are the minority carriers and pentavalent atoms are the dopants. Holes are majority carriers and trivalent atoms are dopants. Okay, so for a N-type semiconductor or a N-type silicon, you should remember that the majority carriers are your electrons, okay, and the minority carriers are the holes. So this is for a N-type silicon, okay. This you should remember as a fact, okay. For your easy remembering, I'll give you N-type means a negative type you can assume, and in a negative type, the majority carriers are negative, that is electrons, okay. So just sort of memory aid that N-type has a majority carriers as electrons and minority carriers as holes. Okay. And what about the doping? N-type semiconductor is obtained by doping, that is the dopants. The dopants have the pentavalent atoms. Okay, the dopants are your pentavalent atoms like phosphorus. Dopants are your pentavalent atoms like phosphorus. Okay, so these facts you have to know about the N-type silicon. So uh, now returning to the question, so our answer, which is the true statement, right? Electrons are majority carriers, okay, and trivalent atoms are dopants. No, this should be pentavalent atoms, right? This should be pentavalent atoms. Okay. Next, electrons are minority carriers. No, and pentavalent atoms are the dopants. Yes, this is right, but these electrons are the majority carriers. Okay. Next, holes are the minority carriers. Yeah, minority carriers are the holes. And the pentavalent atoms are the dopants. Yeah, this statement is absolutely correct. And it's the last option. Holes are majority carriers. No. Trivalent atoms are dopants. Again, no. Holes are your minority carriers. Okay. And pentavalent atoms are your dopants. Okay. So I really hope that you guys will remember these three facts about a N-type silicon. Okay. So if this question is clear to everyone, let's move on to the next question for today, right? Okay. So here comes the next question. Again, a multiple choice question only. This question statement or this question stem is actually the previous stem only, 14.1, N-type silicon, which is true. Electrons majority trivalent movement. So this statement is the same. But the second question actually is, which of the statements, sorry for that, which of the statements given in exercise 14.1, okay, is true for a p-type semiconductor? Okay, is true for a p-type semiconductor. The previous question was for an n-type semiconductor. Now it's the opposite. It's asking for a p-type semiconductor. Okay, so let's write again for the p-type semiconductor as we did in the previous case for the n-type. Okay, so for a p-type, okay, we have the majority carriers. P-type means a positive type, you can say. So the majority carriers will be positive, right? And what is the positive entity? They are the holes, right? So majority carriers would be holes and minority carriers. It's just the reverse of the N-type case, right? Minority carriers would be your electrons, okay? And your dopants would be your trivalent atoms, okay? There it was pentavalent. So after completing a valency of 4, one extra electron would be left out, right? That's why this extra electron is the majority carrier and it's an N-type. But if it's 3, it's a trivalent, then it's one electron deficit, okay? So that makes it positive charged, and this deficit is actually called a hole, right? Which is the majority carrier in case of a p-type semiconductor, isn't it? So the dopant will be a trivalent atom like aluminium, okay, in silicon atoms. Silicon is the like the base substance, and in that we dope with your trivalent atoms, okay? Trivalent atoms in silicon atoms. Okay. So we'll check the options again for a p-type semiconductor this time. So here I'm making it P, okay, for a p-type semiconductor, which is true. Electrons are majority carriers. No, electrons will be the minority carriers in this case. Okay. And trivalent atom are the dopants. Okay, this statement is right. Electrons are the minority carriers. Okay. And pentavalent atoms are the dopants. No, we have the trivalent atom as the dopant, right? It's the trivalent atoms. Holes are minority. No, holes are majority carriers. Holes are majority carriers. And pentavalent atoms are the dopants. No, they are the trivalent atoms. Okay. The trivalent atoms. Holes are the majority carriers. Correct. And trivalent atoms are the dopants. This is also very, very correct. So the answer is option D. Okay. So I need you to remember these three facts about both p-type and n-type semiconductors. Okay. Once again, p-type, this will also be useful for your NEET exam. Okay. N-type, majority is electron, minority are holes, dopants is your pentavalent. And for your p-type, majority holes, minority electrons, dopant is a trivalent atom. Okay. And you always remember this thing, then you did not mug up. You can also think conceptually. Okay, great. Now, I guess these two questions are clear to everyone. So we will move on to the next question. That's okay. So the third question says carbon, silicon, and germanium have four valence electrons each. Okay, everyone knows this. Okay, carbon, then below that lies silicon, below that lies germanium in the periodic table. Okay, so they have four valence electrons each, six group elements, right? Now, these are characterized by valence and conduction bands, the valence band theory. Okay, the valence band theory in semiconductors. Okay, there are two bands, right? By the valence band and the conduction band. Okay. These are separated by energy band gap respectively, which is equals to energy gap of carbon, energy gap of silicon, energy gap of germanium. Okay. Now, which of the following is true? That means what is the relationship between these gaps? Okay. Now, for the question, uh, always remember that as this atomic number goes on increasing from carbon to silicon to germanium, the energy band gap goes on decreasing. Okay, so it will be the energy gap of carbon would be the energy gap of silicon more than energy gap of germanium. Okay, that is this energy gap is like inversely proportional to your atomic number. You can remember for solving your next questions. Okay, when such type of questions arise in future, you can remember this thing. Okay, so the option which comes out to be true is your third option. Okay. So yeah, guess this is just a factual, or you just need to remember this. It's nothing conceptual over here. Okay. It's the valence band theory. Okay. It's the valence band theory. Okay. Great. Now let's move on to the next question, fourth question for today, which says, in an unbiased, okay, PN junction diode, okay, holes diffused from the P region to the N region, okay, because asking the reason why holes, which are the positive charges, which are the majority carriers in the P-type semiconductor, they move from the P region to the N region because free electrons in the N region attract them. They move across the junction by potential difference. Hole concentration in the P region is more as compared to the N region and all of the above. So, which is actually the correct option. Okay. Now, uh, see, the thing actually is how microscopically how this thing works is if this is, let me draw a P-type. Okay. This thing is P-type, assume this plate, and attached to that, I have my N-type. Okay. So this is the PN junction diode. Okay. All right. This is N-type and this is P-type. Okay. Now, this P-type, the majority carriers are the holes, right? The majority carriers are the holes. Okay. And in the N-type, the majority carriers are your electrons, right? We'll call them with dots. The excess electrons of the pentavalent dope bands, right? The electrons are the majority carriers. Okay. So now what happens? This is a P-type and this is an N-type, and it's an unbiased. Okay. So that means there is no electric field or potential difference being applied across this PN junction diode. It's just kept like this only without any application of external electric field. Now think, when you just bring them to close to each other, or if you approximate these to each other, this has a positive charge, okay, and this is a negatively charged electrons, right? And this is a hole, like this is a space you can think of. So what happens? These electrons will get attracted and they will fall into these holes, you can sort of say. Okay, for your understanding, they will fall into these holes. Okay, next, uh, these will migrate here. Okay, these will migrate here and these will come here. Okay, so like this. Now, why does this happen? Because here is the positive charge, here is the negative charge. So the overall electric field, I mean, just at the nearby region, okay, just at the nearby region, just in this region, you can say, very, very close to the uh, touching point of the diode, there is an electric field. Okay, not throughout the entire plate. Okay, just where these two plates touch each other, there is an electric field, okay, and that field will be directed where? Yeah, so this is the positive side and this is the negative side. So this electric field will be directed here, okay. Now, holes are not particles, right? Holes are not particles. The electrons are actually the particles that can move, okay. So what happens? Due to the electric field directed this way, is the electron is a negatively charged particle. So the force on the electron will be the other way, okay? And these electrons just fall into this holes, okay? So now if the electron goes, okay, from this side to this side, here what is created from the previous place? A hole will be created, right? Because it will become electron deficient here, okay? Because the electron moved away. So here new holes will be created. So the end result will be here the electrons have come, okay? Electrons have come over here and the holes have come over here. That looks like the holes have migrated, okay? All right, this is what happens microscopically at the junction of a PN diode, okay? Now, uh, the usual tendency of the charge carriers is actually to disperse towards the lower concentration region from the higher concentration region, okay? Just like a diffusion sort of thing, okay? Here the holes are in maximum concentration and here the electrons are in maximum concentration, okay? So it can be said that in an unbiased PN junction diode, okay, holes disperse from the P region to the N region as the P region has a greater concentration of the holes than the N region. Okay, so the correct answer to this question is C. Okay, and what actually happens at the microscopic level, I have told you here. Okay, this is the junctional electric field, if you can call it. This is known as the uh, junctional electric field. All right. Great. Okay. Now, I hope this question is clear to everyone. So let's move on to the next question for today. The next question says, when a forward bias is applied to a PN junction, okay, it raises the potential barrier, reduces the majority current to zero, lowers the potential barrier, none of this. Okay. Now, uh, see, uh, see, this is a PN junction. I'll draw it again. This is suppose the P plate, okay? This is the P plate, okay? And this is the N plate, okay? This is the P type and this is the N type, okay? Now, before applying the bias, okay? Before applying the bias, uh, what do we have? Before applying the bias, here holes are maximum, okay? And here your electrons are maximum, okay? At the junction. And a net electric field used to exist like this, okay? When it was an unbiased situation, okay? Now I apply this potential difference, okay? I apply a potential, it's a forward bias, okay? So I apply some potential difference, okay? Forward bias means the positive plate is connected to the P type. Okay, that's the forward bias. So this is positive now. This is negative connected to the negative end. Okay. Now what will happen? The electrons will fall into here. Okay. And if the electrons fall into here, uh, slowly what will happen? This side will become more and more becoming positively charged, and this side is becoming more and more negatively charged. Okay. So in a sense, what is happening? The signs are reversing, right? Initially, this was all positive, but now this is all becoming negative. So there will be a change in the direction of the electric field also, right? The electric field now will point to the left side, okay? Or it is beginning to decline in strength towards the right side, okay? Now the decline in strength of the electric field also means that there is lowering of the, that is lowering of the potential barrier also, right? Lowering of the potential barrier. The electric field strength is directly proportional to the potential barrier, isn't it? So if the electric field strength in this direction is reduced, so the potential barrier is also going to be reduced. Okay. So it is lowers the potential barrier is the right answer to this question. Okay. I guess everyone is comfortable, cool and comfortable with this explanation. Okay. So let's move on to the next question or the last question for today, which is uh, in half wave rectification, okay, in a half wave rectifier, what is the output frequency if the input frequency is 50 hertz? And what is the output frequency of a full wave rectifier for the same input frequency? Okay. So, first, in case of a half wave rectifier, okay, for the case of half wave rectifier, uh, always remember that the output frequency always equals the input frequency. Okay, this is a fact you need to know. And for a full wave rectifier, for a full wave rectifier, okay, the output frequency, the output frequency equals 2 times the input frequency. Okay, so these two facts you need to remember. Okay, half wave and full wave rectifier. So in the first case, the output frequency will be equal to the input frequency, which is 50 hertz only. And in this case, in the full wave rectifier, it's 2 times the input frequency. Okay, so it will be 100 hertz. Okay, so yeah, I guess you understood. You just need to remember this formula. Okay, then you are good to go. All right. So with this, we finish your semiconductors chapter, NCRT solutions. Okay, all were MCQs only, almost 5 MCQs. One was just formula-based application. Okay, and apart from all these questions in the new NCRT, actually the logic gates part has been omitted. Okay, in the exercises. That's why we aren't discussing those here. But logic gates, AND gate, NOR gate, NAND gate, these all are very, very important in the NEET UG and your JEE mains. Okay, this chapter is excluded from JEE Advanced, but in NEET UG and JEE mains chapter, for NEET UG and JEE mains preparation, you have to read your. I'll write out here. Okay, once you should be thorough with your logic gates. Okay, the logic gates and your Boolean algebra, right? So logic gates and Boolean algebra for NEET UG and JMeans. Okay, J Advanced, this part has been deducted. Okay, not for J Advanced. Okay, so with this, let's end today's session. I hope you guys benefited a lot out of it. Okay, and last but not the least, before ending the session, I would like to again implore you guys, whoever has been inspired watching these sessions be on YouTube and want to take a dedicated, full guided course for your NEET UG or JEE Mains preparation in a very dedicated and in a proper flow, in a proper manner with one-to-one guidance, then please feel free to contact us by the contact number given below in the description box of this video. All right. So thank you guys for your patient hearing, and very soon we'll return with next set of video. Okay. So till then, have a good night. Tata.